Hello, everyone. Welcome back. Today, I'm going to be talking about scatter plots and linear correlation. So, what is linear correlation? Linear correlation it says where variables x, comma y have a linear correlation if changes in one variable tend to be proportional to changes in the other. So, let's talk about in these scenarios for the following scatter plots, let's describe the relationship between the two variables shown, right? And I want to make a point here about linear correlation that means that if it's something is linear, then that means as x increases, y also increases or decreases, right? So as x increases, y increases or y decreases, right? If it's a negative correlation. Whereas there's going to be correlations that aren't very linear, right? Or there's going to be times when we don't have any linear correlation whatsoever. Where the points kind of just seem a bit scattered and not really as though they have a pattern to them. So let's talk about that. So this first one, well, this looks relatively linear, right? I could draw a line here and it doesn't completely go through all the points, but this is relatively linear, right? This is approximately linear. So I'm going to say this is a strong positive linear correlation. Strong positive. This one here, this looks like an even stronger negative, right? This looks like, we could connect the dots and we'd have a line. So this is a strong negative correlation. This one here looks like there is no correlation. It just looks like a bunch of dots randomly. It's not really clear that as x increases, does y increase or decrease? Not really either of them, I would say. So we would say no correlation. How about this next one? Well, I think it's not very strong. I would say maybe it's more moderate than strong. Maybe might be like a moderate to weak positive. Because it is still going up in a linear fashion, but it kind of goes off track at different points. So it certainly does have some linear correlation to it, but definitely not as strong as the strong positive that we see above. This next one here looks to me like a weak positive. It's even weaker than the other one that I had described before as moderate to weak. So I would say this is a weak positive correlation because it's still going up, but again, we kind of have them somewhat scattered. And then this last one here, I would say this is definitely a negative. This would be, I would say, strong to moderate. It's a bit weaker than the other strong negative we saw and the other strong positive we saw, but it's certainly much stronger than the moderate to weak positive that we looked at earlier. So there we have it. So there's going to be times when we have, strong positive correlation, strong negatives, no correlation, positive, moderate, weak positive, and strong or moderate things. So I'm going to try and give an example for each of these. Let's start with what has a strong positive correlation. Something that's directly proportional, right? So an example of this would be how much money we're spending as the x coordinate versus how much gas is going into our car, right? That's going to be strong positive because the more gas that we put into our car, the more money it's going to cost, or the less gas that we're putting into our car, the less money it costs. So that would certainly be a strong positive correlation because it's very directly proportional right away. All right, so for strong negative, an example could be that X is, how much does it rain? And Y could be how much do we have to water our garden, right? Because the more that it rains, the less we're going to water our garden. And the less it rains, the more we water our garden. So that could be an example for strong negative, or, just negative in general. Now, what about no correlation? A good example of no correlation would be two things that have nothing to do with one another whatsoever. So, for example, math mark versus hair length, right? Someone could have long hair and have a great math mark, or short hair and have a great math mark, or vice versa. Someone could have long hair and a bad math mark, or or short hair and a bad math mark, right? So the length of our hair versus how well we're doing in our math class, those two things have nothing to do with one another. So likely there's not really going to be any correlation with that. Now, what about like a moderate positive or a weak positive? I'm going to kind of lump these two together and give some examples. So, one example of this would be age versus height, right? Because we know that overall, as we get older, especially from 0 to 18, that the older we get, the taller we become overall, right? And same with other people. However, that doesn't mean that everyone who's the exact same age is going to be the same height, right? Sometimes someone might be a slightly older but shorter than someone who's younger, or vice versa, right? Someone might be a little bit younger but still taller. However, overall, on average, we know that the older someone is, on average, the higher the height will be, right? If we took the average of all the third graders, that average would be a lot lower than the average of the fifth graders. However, there would still be some individual third graders who might be taller or the same height as some individual fifth graders, just because everyone has different genetics and comes from different family backgrounds. And so some people are going to be taller or shorter than others, right? So that's an example of moderate positive, where overall in general, as time goes on, this happens, this picks up, and so on, but not always. It's not always perfect. All right, now what about a strong or a strong to moderate negative? Let's say one example for this could be like the lower the temperature, the more clothes we might have to wear, right? Because if the temperature gets really, really low, we're probably wearing more layers. And if the temperature is high, then we're going to be wearing less layers, right? However, again, this might vary a little bit from person to person, right? There's not, if it's 10 degrees outside, this is the set number of layers everybody must wear. Well, no. There's going to be different people wearing different numbers of layers there, but overall, they'll be more similar than, at a time when the weather is 30 degrees. On average, people are going to wear a lot less layers for 30 degrees, probably just the one layer. So yes, that could be an example for a strong or a moderate negative one there. Okay, so let's move on. I hope those examples were helpful and that this is making sense. Um, let's move on and talk a little bit more, go in more detail about this. So it says to get a numerical value for the linear correlation between two variables, we can find the linear correlation coefficient, which is denoted as R, right? So a strong negative linear correlation would be have a coefficient of -1 to -0.67. And if it's exactly -1, that means it's a perfect negative. So that means it's, a perfect negative line, right? So a line with a slope that has you know, no variance whatsoever. For lack of a better word there. And then moderate would be from -0.7 to -0.33. And then from -0.33 to 0, it would be a weak negative linear correlation. And same with positive, right? If we have 0 to 0.33, it's going to be weak positive. 0.33 to 0.67 would be moderate. And then 0.67 to 1 would be strong. And if we have 1, then that's a perfect linear correlation, right? So something like, let's say it costs $2 per chocolate bar, and there's no discount or anything like that if you buy more or something like that. So in that case, it would be directly proportional. It would be a perfect positive linear correlation where the amount of money you spend is directly proportional to how many chocolate bars you bought that day. Good. So what is the formula for the correlation coefficient? So it's this formula here, and you know what? This formula might look daunting, and so I want to talk a little bit about what this formula means. So n, first of all, n is our number of data points. Okay? Number of data points. Okay? And then here we have the sum of x times y. So basically every x and every y, we multiply them together, and then we're going to add up all those results, right? Going back to summation notation. And then we're going to subtract off the summation of all the x values times the summation of all the y values. Okay, so that's what those two are there for. And that's over the square root of n, so again, number of data points, times the sum of all the x squared values. So we would take all the x values, we would square them, and then we'd add all those numbers together to get this number here. Then for this one, this one is different. This one is the sum of all the x values squared. So up here, we already would have found the sum of the x values. So we just have to take this number and square it. And so this is a common mistake I see people making. I see people saying, oh, we can cancel these out. They're the same thing. But no, they are not the same thing, right? One of them is where we have to square all the values first and then add. The other one is where we add all the values first and then square. And those two things are not necessarily going to give us the same number. In fact, most times we will not get the same number out of them. And then same thing with y. We're going to multiply that by n. So again, number of data points, and then we're going to add up all of the y squared values, and then we're going to subtract all the y values added up squared, right? So again, remember, these two do not cancel out. These two are two different separate things, so that's important. So this equation is very long and it might look daunting, but as long as we understand what exactly summation notation is, what we mean by it, then we are going to be just fine. We're going to be able to figure it out. Okay, so with that said, let's do an example for this one. And up here, they put the formula again because we are going to need it for this question. If there's a formula sheet, I would hope this formula would be on it. However, you'd also be surprised as to how quickly you pick up on these formulas after just doing a few questions with them. You get into the routine of doing it, and then you just kind of know the formulas as well. Okay. So this one here says Chris Korn wants to determine the relationship between the mean temperature during the growing season and the size of his corn crop. The data below is for the last 6 crops. Find the linear correlation coefficient between the mean temperature and the yield for the season. Okay, so what do we want to find essentially? We want to find R. Now, how do we find R? Well, we've got to first find the following things. We need to find the summation of x times y, right? Which means we have to find out x times y for all of these and then add it up. We also need to find what else? We need to find the summation of e to the x, right? We need to find the addition of all the x values, which that's pretty simple. We would just add them all up. We also need to find summation of all the y values. So we'll put that number here, we'll put this number there, this one here. And then we also need to find what else? A few more things. We need to find all the x squared values and add those up. And then we need to find all of the y squared values and add those up. Now notice I didn't say anything for this one specifically because all this is the summation of all the x values squared and then the summation of all the y values squared. So these are just numbers we'll already have, right? It'll just be, this one will just be the blue number squared and this one will just be the green number squared. And so those aren't really any more work for us necessarily. Well, not really. It's not very much extra work to to just square something, right? So yeah. Okay. All right, so let's go ahead and start. So first I'm just going to add up all the x values. Let's say this is our x and this is our y. So let's grab a calculator. I'm just going to add them up. So 4 plus 8 plus 10 plus 9 plus 11 plus 6 equals 48. Okay, so therefore we know that if we add all these up, we get 48. Good. All right, the next one is we must add up all the y values. So what do we get if we add up 1.6 plus 2.4 plus 2 plus 2.6 plus 2.1 plus 2.2? We are going to end up with 12.9. So this is going to be 12.9. Okay, now we need to find all of the purple values, so all the xy values. Over here, this will be the x squared values, and over here, this will be the y squared values. All right, so let's do it. So what is x times y in this case? 4 times 1.6 is 6.4. Okay. What about 8 times 2.4 is 19.2. Okay, 10 times 2, well, that's 20. We know that one. 9 times 2.6 is 23.4. 23, let's see, 11 times 2.1 would be 23.1. And lastly, 6 times 2.2 is 13.2. Okay, so now we've got to add all of those values up. So let's add them up. 6.4 plus 19.2 plus 20 plus 23.1 plus 23.4 plus 13.2 is going to give us 105.3. Very good. Okay, let's do the x squared value. So 4 squared is 16, 8 squared is 64, 10 squared is 100, 9 squared is 81, 11 squared is 121, and 6 squared is 36. Now we've got to add up all of those values. So let's see, 16 plus 64 plus 100 plus 81 plus 121 plus 36 is 418. So that's 418. Amazing. And then the y squared values. Okay, so 1.6 squared is 2.56. Beautiful. Okay. 2.4 squared is 5.76. 2 squared is 4. That one we know. The next one, 2.6 squared is 6.76. 2.1 squared is 4.41. And 2.2 squared is 4.84. Good. Amazing. Okay, so now I'm going to add up all of those values. 2.56 plus 5.76 plus 4 plus 6.76 plus 4.41 plus 0.84 is equal to 28.33. Awesome. So now we have all the values we need. So now all we've got to do is plug it into the equation. Okay, so this has to do with n, which n is 6, right? There are 6 different crops that we're measuring. So r is equal to 6 times, the summation of x times y, which is 105.3, minus the summation of x times summation of y. So that's 48 times 12.9, right? Okay, and that's over the square root of 6 times the summation of the x squared values. So that's 418 minus, minus the summation of the x values squared, which that's just going to be 48 squared, right? Okay, and then that is going to be multiplied by 6 times the summation of the y squared values, which is 28.33, subtract the, the addition, the summation of the y values squared. So 12.9 squared, 12.9 squared. So this is just the step where we would plug all of that in, right? So we got to do that. We've got to plug everything in. And then what we're going to do is we're just going to solve this. We're going to end up with, let's see, 631.8 minus 619.2 over the square root of 2508 minus 2304. times 169.98 minus, let's see, 166.41. Let's make our lines. There we go. That's better. That's going to be, let's see, 12.6 over the square root of 204 times 3.57, which is going to be equal to 12.6 over 26.99, which is equal to 0.47. Okay. And the original question was to find this and also find the linear correlation, basically come to a conclusion about what we found. So if we go back on here, 0.47 is, in between 0.33 and 0.67. So that means that it is that there is a moderate positive linear correlation. So therefore, there is a moderate positive linear combination, correlation, not combination. We'll learn about combinations later, but for now we're learning about correlations. But there we have it. So this question wasn't hard, but this question, it had a lot of different parts to it, right? It was time consuming. So like graphing, not necessarily difficult, but definitely time consuming, I think, is the big constraint with this. I would suggest practicing a few of these. I wouldn't suggest practicing more than, 2 or 3 of these in one sit, because, it can get frustrating after a while, just because it's a lot of little nitpicky things to do. It's just to find out every value to plug into your equation, takes the majority of the time as opposed to actually solving for it. So so this is a big one. But that is it for this lesson about linear correlation. Next time we'll talk about linear regression. So we'll talk about that next day. Have a good rest of your day, everyone, and we'll see you in the next class.